Okay, so we're going to start in this video with a triangle, this blue thing here, and I'm going to compute its first isodynamic point, x15, and I'm going to rotate this triangle about its first isodynamic point, like so, rigidly rotated. Now, what I'm going to do is I'm going to introduce an inversion circle. It's sitting here on the right. Let's scale this down a bit. I want to place it toward the right here of the triangle for reasons that are going to become clear in a little bit. All right. Now, I want to actually draw a new triangle. This red thing here, whose vertices are inversions of the blue vertices with respect to this inversion circle, this dash green inversion circle. And let's go ahead and centralize or center the scene. Let's scale it up a bit. Now, first thing you notice here is that x15 to the minus 1, which represents the first isodynamic point of the inversive triangle, the red triangle, is collinear with the center of inversion and the isodynamic of the blue, the first isodynamic of the blue. Now let's rotate the blue. So you get this beautiful phenomenon, which we saw before in a previous video, when on the left side I had the psi median x6 and on the right side I had the psi median of the red. The same thing seems to be happening here for the first isodynamic point in this particular configuration of the inversion circle. Okay, inversion circle is sufficiently to the right. Now notice that when this is the case, the red family is never undergoing an eversion. Okay, an eversion with an E, meaning that, you know, it's never the case that the long side is actually sliding through the opposite vertex. And the reason this is the case is because the circumcircle of the blue triangle family will never be such that it will contain the center of inversion. Okay? Now, if I now approach the inversion circle and I move it to the left, in such a way that this family of circumcircles here, these blue dash circles, can actually at some point gobble up the center of inversion, this is going to cause the red triangle to undergo an eversion, and you will see what happens. So let's now slowly move this guy to the left. So the blue is still not going through, the blue circumcircle not going through, so my x15 of the inversive is still stationary. Now, if I'm now sufficiently close, and I actually want to draw simultaneously the locus of x15, so I'm going to click this here and I'm going to move my center of inversion sufficiently close to the left. Okay, so we start getting a non-stationary locus of f15 of the inversive. And this thing is very curious. Let's do this. I'm going to move the circle of inversion a little bit further to the left so we can see what's happening to this magenta locus of x15, which actually comprises two phases. So let's move this inward still, like so. Let's make it like that. I'm going to exaggerate this proximity of the pivot point x15 of the blue and the center of inversion, so we can actually understand, and let's exaggerate this even further, like that. Okay, and let's move this to the left. Now you can see here that this looks like a delta-shaped figure. So what is this? This is the locus of f15 of the inversive. Let's take a look at what's happening to the f15 of the inversive. It's a very curious bistable motion, okay? So let's try to break this down, okay? There's two states for the motion of x15 of the inversion, okay? When the circumcircle of the original family does not contain O, the center of inversion, we go back to the initial situation. The locus of f15 inversive was actually stationary. So let's slowly observe that. You can see here that this blue circumcircle is actually rotating counterclockwise, and as it rotates counterclockwise, O is going to be exterior to the circumcircle. So during this period, x15 of the inversive is stationary at this tip of this delta curve. Okay, now as we approach a situation where the blue circumcircle is gonna come near and in fact turn the center of inversion as an interior point, what's going to happen is something quite curious. This stationary point here, x15 of the inversive, is going to discontinuously jump from this point over to this point, okay, to this tip of this arc of a circle, this inverted arc of a circle here. This is actually a perfectly circular arc, but it's actually going to discontinuously jump. So you can safely ignore this artifact here, this straight line that is connecting this stationary phase of the locus to this non-stationary circular arc of the locus. You can ignore this straight line as a graphical artifact. Okay, I'm drawing the locus as a polygonal curve, so this is actually a straight side of the polygon, but it actually doesn't exist. There's an actual discontinuous jump, and that's going to happen exactly at the moment where this blue circumcircle turns this stationary center of inversion as an interior point. So let's go ahead and see if I can do this manually, right? I'm at 69, so I'm going to make it be 70 here, perhaps, so that I'm a bit closer, 71 degrees, 73 degrees, 76, 78, and now you can see here that my circumcircle is almost touching the stationary center of inversion, and x15 is still put at the tip of the delta curve, the delta locus, but at some point, 81, 82, 83, okay, we're about to make O become interior. Oops, okay, so x15 has jumped. And in fact, it did not jump to this tip of the arc, it actually jumped to this top tip over here. So again, you can ignore this. Now look at what's happening to my inversive triangle, okay? Since my inversion center is on the circumcircle of my original family, the inversion is going to be a degenerate straight line polygon. And this is precisely where the eversion of the red family is taking place. Now once this is achieved, okay, and now let's go here to say 93, my inversion center now is safely interior to my circumcircle. You can see here that the red triangle is no longer a segment polygon, and it has undergone its eversion, and now x15 is going to follow along a circular arc. So x15 is no longer stationary. So let's accompany that. Let's make this be very slow. Yeah, let's make this motion be extremely slow, even slower than that. And you can see here that my circumcircle contains O. x15 of the inversive is following along this path. Okay. The red circle is its circumcircle that we're disregarding for now. We're only caring about the circumcircle of the blue. Okay, and you can see here that it's following along its merry circular arc path. Okay, until we hit the symmetric case where, as you can see here, O is going to become now exterior to the circumcircle again. So x15 inversive is approaching the tip of its circular arc portion of its locus. And then at this extreme situation like here, my triangle is going to evert back. The inversive triangle, it everts back. And then suddenly I jump back to that tip. So now my circumcircle is again exterior to the family. So the center of inversion exterior to the family of circumcircles, and x15 is put. So this is a really interesting locus in that it comprises an isolated point where x15 of the inversive stays put for a while, and it comprises a circular arc. Okay, so the circular arc is activated precisely when the circumcircle of my blue family makes it so that O jumps to its interior. So it's going to happen just now again. There you go. So x15 again is following that circular arc. And then, so we repeat this phenomenon again. As the blue circumcircle rotates counterclockwise, it's going to come to a situation where the red polygon is going to evert and O is going to become exterior, and x15 is going to be at the tip of the arc, and then it's going to jump to that stationary location. So this is almost like an astable multivibrator in the sense that you have two states, and one of the states is stationary and the other state is moving. So it's a very fascinating locus. Okay, now let's continue to actually move O inward. It's going to continue to move O inward, closer to this stationary pivot point x15, and let's see what happens. As I continue to move O inward, okay, I'm still in the same situation. Let's go ahead and move this whole scene here a little bit to the right. Let's scale this down so we can see the whole scene. And what I'm doing is I'm actually continuing to move O inward, okay? So let's scale this up a bit again, and let's continue to move O inward. So I'm going to continue to move O inward. And then you hit another kind of a critical point where that circular arc, which continues to be circular, now self-intersects with the discontinuous jump. Okay, so let's watch this just for curiosity's sake. So you can see here x15 is still along its circular arc. This circular arc is going to self-intersect the discontinuous jump, but we're going to get the same phenomenon. It's just that this is a more pronounced circular arc, which I can even exaggerate a bit more. Maybe not. Okay, so here's it exaggerated even a little more as I move it to the right, to the left. Okay, now we're going to undergo another very interesting critical point of this locus, which is where the center of inversion is so close to the stationary x15 of the blue that now no longer will the circumradius be able to expel O from its interior. So this is about to happen here. So you can see here that we still have two states as I animate this. We still have a state where O is interior and where O is exterior. But you can see here that O being exterior is very short-lived. Okay, so here's the exterior O situation right here. And again, what does this correspond to? When O is exterior, we know that x15 is stationary, right? So x15 is stationary, but that's becoming a briefer and briefer period of time. So now if I actually nudge O inwards, this is going to cease from being possible. Let's do that, and let's see what happens when I do that. So I just nudged O a little more to the interior, so we're actually coming close to the transition. You can see here that I still have this very pronounced arc of a circle, and then I have these two discontinuous jumps that place x15 very briefly at the tip of the discontinuous jump. So you're going to see here that it's right there, it's at the tip, but it's very brief because O can only stay exterior to the circumcircle right now very briefly. You see, O is going to be exterior to the circumcircle very briefly. And let's see if I can do that. Hopefully I'm not going to, yeah, there it is. So it's briefly exterior. Now if I nudge O just a tad to the left, look at what's going to happen. Let's do that. Okay, so now I've sort of gone past the critical point, and now O is permanently interior to the circumcircle. So let's go ahead and exaggerate that a little more. And when that happens, that arc of a circle actually closes up, it gobbles up the discontinuous jump, and the path of x15 now is permanently a circle. So long as the relative position of my inversion circle and the pivot and my, the geometry of my triangle is such that now the circumcircle of the triangle always encompasses O, okay, or O is always interior to the circumcircle, the path of x15 is permanently a circle, okay? Now what happens if I keep moving O to the left? Let's do that. And I just have to avoid the situation here where O is exactly equal to x15 because that causes some instability. So let's see here. I'm going to make this x16, x15. Yeah, let's keep doing this. Let's make it be 11. So I'm pretty close to x15. Let's make it be 0.09, 0.07, 0.06. So I'm pretty close, right? At some point, O is going to be equal to x15. And I don't want this to happen to avoid instability. But you can see here that O is safely inside of the circumcircle. And I continue to have a circular locus of my x15, right? Okay, now let's cross over to the other side of x15, trying to avoid that. So I'm going to make this be minus 0.05. 0, 5. There you go. I'm on the other side. I'm still circular. You can see the magenta curve. And right here I'm showing that numerically this thing is a conic or it's an ellipse where A and B are equal. So the aspect ratio of this conic is 1. So I can say, okay, this thing is a circle. And this is why I've been telling you guys that we're in a circle situation here. So let's keep going to the left now. I can safely now move this guy to the left manually, like so. And let's see what happens. There's a symmetric transition here, right? So you can see that there's going to be a critical point which is going to cause now that same phenomenon but now symmetrically to the left. So now you have two phases. You have x15 moving along a pronounced circle. It's going to now briefly stay at that tip. Let's look at that tip and let's exaggerate this a little bit to the left so we can now mirror the phenomenon that we had before. So now we have these two phases, but they're happening on the other side symmetrically, okay? And now x15 is moving along a circle and it stays put at the tip right here for a while, and then it moves up and it stays put, moves up along this circle, then it stays put there. So of course, if I move OX further to the left, I just get less and less pronounced effects. At some point, I'm going to go back to that other situation where O can no longer be interior to the circumcircle. So now I have the mirror of what we started with. X15 is a point. Now, briefly before we end, I'm going to show you guys that you get the exact same phenomenon with the second isodynamic point, X16. And to do that, I'm just going to choose X16 here. And we're going to move OX in such a way that, there you go. So now, you can see here that I'm pivoting the blue triangle about its x16, and recall that the second isodynamic point is the inversion of the first isodynamic point with respect to the circumcircle. So if the first isodynamic point, so here's x15, right, is interior to the circumcircle, the second isodynamic point must be exterior because it's the inversion of x15 with respect to the circumcircle. But it's here, and I'm making the blue family rotate about it. Okay. Now notice that x16 of the inversive, sorry, let me say it this way. Notice that the circumcircle of my original family is always maintaining O exterior to it. Therefore, x16 is going to be stationary. Let's now nudge my center of inversion in such a way that it will intersect with this moving family of circumcircles. So let's do that, and you're going to watch what happens. Oh no, okay, I just got to that position that it was trying to avoid right here. And let's see what's happening to this locus. Maybe I'm moving in the wrong direction. Yeah, so x16 has crossed over to this side now. Let's see what's happening here. So yeah, so let's go ahead and trigger this situation and let's try to analyze it. Okay, so I have this magenta locus of my inversive x16. And this is just some polygonal sampling. If I change the step of my locus computation, you can see that this is a very neat and circular arc. I can affirm that this is a circular arc because this is eventually going to turn into a full circle, depending on where the center of inversion is. But let's just follow the dynamics of this. Okay, so let's actually change this sampling. Let's maintain that very sort of more rough sampling here. You guys can just think that this is a perfectly circular arc, but this is just going to allow us to see the animation more smoothly. So look at what's happening now. The circumcircle of my blue family, or the center of inversion, is still exterior to the circumcircle. Therefore, x16 of the inversive of the red family is stationary, right? Now watch what happens when the center of inversion becomes interior to the circumcircle of my family. Again, we have the same phenomenon. We have x16 of the inversive now moving along a circular arc up until the circumcircle now O exits the circumcircle family again, and x16 is again stationary. So we have the same kind of phenomenon that we experienced with x15 of the inversive. You have two states. Can we get the other set of phenomena? Let's see here. So let's move OX a bit to the right, and let's see what happens here. Okay, so the path is going to invert, and can we make this path ever a perfect circle? Perhaps we can't, okay? Perhaps we can't make this path ever a perfect circle. Let's see, because this is x16. So for that to happen, I would have to ensure that x16 is dynamically interior to the I would have to ensure that the center of inversion were permanently interior to the circumcircle, and I can't do that with x16 because x16 is always exterior, so it's more of a distal kind of a center point. So it looks like with x16 I only have two cases. I either have a point locus like that, where the circumcircle can never include the center of inversion, which is this case here. So x16 is dynamically a point. Or I have a second case, and I'm just doing this experimentally, where you have two states. You either have a moment where the dash blue circumcircle encompasses the center of inversion, or when it does. It doesn't look like I have a possibility to make the center of inversion be dynamically and permanently interior to the circumcircle family. Therefore, I'm never going to get that strictly circular phenomenon that I got with x15 to the minus 1. Okay, so this video was about these very neat phenomena of both isodynamic points, of an inversive image of a family of triangles rotating about either one of their isodynamic points. What happens if I don't rotate about either one of these isodynamic points, but I keep tracking the isodynamic point of the inversive, as we did with x with the side-median point? So let's do this. I have this control here. I can change my rotating center to be. Let's perturb that, right? So let's clear this up so we know what I'm talking about. So yeah, let's get the inversion circle out of here as well. So normally I was telling you guys that I was rotating about x15 or x16, but let's go back to x15. Let's not perturb that. So instead of rotating about x15, I'm going to rotate about something that is close to x15. I'm going to perturb that pivot center, and let's call that z. Let's bring back, so for example, what does that mean? That means that I can now perturb this guy a little bit. So I can do this, rotate about some other point. It doesn't have to be x15 anymore. But what I want to do is I want to track what's happening to x15 on the inversive image. So let's go back to x15. This is actually x15. Let's rebuild our simulation. I'm going to draw the inversion circle. I'm going to draw the inversive image. And this is what I have right now, right? So we're in that situation. Let's draw my inversion circle. Let's move the inversion circle to the right a bit so that x15 can be a point, okay, as we saw before. All right, so let's perturb this pivot center a little bit. Let's see what happens to the locus of x15, which is right now a point. So I'm going to perturb this guy a bit, and I'm going to go over here, for example. Look at what's happening. The locus of f15 of the inversive is a circle. I just perturbed this guy in one horizontal direction. Let's perturb it upwards a bit as well, like that. And look at what's happening. So it looks like in this situation where the circumcircles are not interacting, the locus of x15 of the inversive is a circle. Now let's move the inversion circle inward a bit. And look at what happens. You're now, because of those inversions, okay, you're breaking this up into a few states, okay? And let's try to analyze that just for fun. This looks like it's a bit complex, but I think we can break this down. So I think to do that, we have to draw the circumcircle of the blue family, okay? And you can see here that you have a first magenta arc, which probably reflects the fact that the circumcircle contains O, and then you have a discontinuous jump to a second magenta arc. Okay, let's see why this is happening. So x15 now is in this first magenta arc. Yeah, so we're about to get close to this jump, okay? And it looks like the circumcircle is going to be so that O jumps to its interior, okay? Now let's do this very slowly because I want to see this jump. Yeah, so 8, 30, and we're about to jump. So x15 is reaching the tip of this first arc motion, and now it's going to jump discontinue. We can ignore this straight edge here. This is an artifact. And it's going to jump to this other region here where it's not going to stay stable. It's going to be sliding along it, but I think that too is a circular arc. So let's go 132. So I'm about to jump. 133. I jumped. So what happens after I jump? I stay on that circular arc, right? So we can go 140. And I'm just guessing this is another circular arc. And why do I think that is? It's because O is interior to the circumcircle, so I believe this is going to be a similar phenomenon. 4, 6. So it's moving very slowly there. But I'm curious to know, why is it going to jump again? And is it because O is going to become exterior again? Probably so. 6. So you see that O is about to become exterior again. So let's go 8. And now we're going to become exterior. And we're going to go 60. Okay, so I jumped. So again, O has become exterior. Now, what's happening here, which is different from the previous case, is the following. When O was the exterior, when Z was actually the X15 of the blue family, when O was exterior, my X15 was stationary. If you perturb the family so that the pivot center is no longer X15, then the two states correspond to two distinct motions along two distinct circular arcs. So now O is exterior, okay? I'm going to be moving along this larger circular arc, and then when O becomes interior, I go and move along this other small circular arc. So let's accompany the whole motion. So O is exterior, I'm on the big circular arc, you can see that. O is exterior, I'm not undergoing an inversion. The red family is not undergoing an inversion. It's only going to undergo an inversion when the circumcircle of the blue family passes through O, okay? And when that happens, I'm going to be switching circular arcs. So I'm about to do that. I'm going to be switching circular arcs. I switch circular arcs. I'm on the second one, and then I switch back. So in this situation, actually, your motion is comprised not of a point on a circular arc, but of two distinct circular arcs. So of course, if I move my O a little closer to Z, I will distort this further and further. Okay, but I'm still, let's analyze this motion here. Let's recenter the scene. Okay, and you're going to see here that I continue to be moving along two distinct circular arcs, which are related to whether O is interior or exterior to my family. So it looks like there are two straight line discontinuous jumps that can be safely ignored from this magenta path. And I just hope, yeah, I might have hit an instability here in the numerics of Mathematica. When this happens, I get a freeze. But I think that this pretty much concludes our video. Yeah, I see what happens. So what happens is that the red triangle has become a perfect straight line, and Mathematica is having a hard time dividing by 0. It's probably computing a certain denominator that is 0, and yeah, you can see here that this is happening given the sampling, okay? Yeah, so we get the sense, right? We have this first circular arc here, and we have the second circular arc, and these correspond to states of O being interior, exterior to the blue circumcircle. If I move O further to the left, just to see if there's another topological change, okay? Now look at this. This is quite interesting. Let's move this up a bit. Now what's happening here? Looks like I have this almost straight circular arc, okay, with a discontinuous jump all the way on the bottom, So I have this circular arc. Let's watch this. X15 is moving on this circular arc. Let's increase the step here, make this faster. O is exterior to the blue circumcircle. And then when O becomes interior to the blue circumcircle, X15 is going to jump all the way to the stop area here and move along this second circular arc. It's still a two circular arc motion. Okay, so ignore that jump. All right, so let's continue to move O to the left. Two circular arc motion. Two circular arc motion. So where are these circular arcs? I have this large circular arc here, and I have this other circular arc there, and they are connected by two discontinuous jumps. So you can think of this as two disconnected, disjoint circular arcs the locus, right? The locus is the union of these two disconnected or disjoint circular arcs. Let's move OX to the left a little more. And oh, it's okay. So I can be, if I'm sufficiently close, I thought this was not possible, but if you're sufficiently close, and this has to do with the shape of your triangle, to the center of inversion, then X15 is going to be following a circle. And you can see this here that this is a circle. The reason being that now my circumcircle can never bring O to its interior. Okay, so this is possible as well when I'm deviating a bit from when my center of rotation is not X15 proper. Okay, so let's now move this further to the left, and I'm just going to repeat this as I move this to the left. You just repeat the whole set of states. Okay, and at some point, if you're sufficiently far, you're a perfect circle. So if you're sufficiently far from the center, the pivot center Z, or you're sufficiently close to it, if O is sufficiently far or sufficiently close, X15 is going to be a circle. Okay, is this the case with X16? Probably so. This guy is exterior. Anyway, I think this video contains enough detail and enough experimental exploration of what these loci are. They're super interesting. I'm going to make another video where I'm going to cover a couple more phenomena, X61, X62, and X187. Okay, see you on the next video.